Chapter 9, Input Modeling, Part 2. The process of distribution identification includes three steps. The first step is obtaining a family distributions by assuming independence and identical distribution. And then by having a family of distributions for our dataset, we obtain a specific one by estimating the parameters. Okay, and then by having the parameters, so we have a specific distribution, then we need to see if this specific distribution is a good fit on our data or not. And here we do the test of goodness of fit. Okay. In order to obtain a family of distributions for our dataset, one of the good tools is constructing a histogram. So by having a histogram, we can visualize the shape of the distribution, and then we will see which family of distributions may be a good fit for our dataset. And here are the steps to construct a histogram. So at first we need to divide the range of data into intervals, and then we will label the horizontal axis and also the vertical axis for the frequencies, and then we will obtain the occurrences of or frequencies of data for each interval, and then we will plot the frequencies on the vertical axis. Okay. Obtaining the number of intervals for constructing a histogram is, I can say, it's a challenging part of constructing a histogram. So here we have a rule. The number of class intervals equal the square root of sample size. So often works in practice. So, but usually there is no solid rule here, and we need to have somehow experience and also try different number of intervals to see which one actually can be lead us to obtain a family of distribution. So here, as you see, if we choose less intervals, then we will have too wide bins, right? So it will be coarse or blocky, so like this. So, and we can't actually visualize the shape of distribution, so it wouldn't help us to obtain a family of distribution. And if we choose a high number of class intervals, then we will have two narrow bins. Then the shape like this would be ragged. So again, it's rough and uneven shape, and again, we will not be able to obtain a family of distribution. But if we choose appropriate number of intervals like this, then we can actually somehow visualize what the shape of distribution could be, and then which family of distributions could be a good fit for our data. Okay. We can obtain a frequency distributions from the histogram. If our data is continuous, then we can draw a line through the center point of each class interval. Then it will be a shape like a PDF. I mean, the probability density function of that distribution. Or if we have discrete data, then it will look like a probability mass function. Okay. And so this method, I mean, having histogram by and obtaining the family of distribution using a histogram is a graphical approach. It's simple and straightforward. Need to guess the type of distribution, so it needs somehow a level of knowledge about the distributions, and also it needs experience, I mean, in obtaining the number of appropriate number of intervals. Okay. A family of distribution can be obtained based on the context of the data and also the shape of histogram. For example, if we have data about the inter-arrival times, then since it's about the time and interval time between the arrivals, then we know that for this context, exponential is a good choice, right? And if the shape of histogram here looks like exponential, then selecting the exponential distribution would be warranted for this data set. Or another example, if we have data about weights of pallets of freight, then it's about the weight of pallets, right? And we know that all pallets should be the same in the weight, but there will be variation, there will be deviation around a certain number, let's say. Okay, so for this purpose, we see somehow like this, right? We have a certain number and we expect to have all the weights around that, but we have somehow deviation around that certain number. So somehow this shape would be, is expected to have for the histogram. And if we see this type of frequency diagram on the histogram, then normal distribution would be warranted for this data set. Okay. So here we have a review on the features of some popular distributions. I'm not going to actually explain all the distributions here because you had a review on these distributions in chapter 5 in tutorial session. So I'm going to actually explain more for some of these distributions which are more common in simulation. For example, the Poisson process or Poisson distribution, if we have a unit, let's say for space or for time, let's say for time, for example, a time unit of 1 hour or a time unit of 1 minute, and then we're interested in study of the number of events are going to be occur in a time unit. For example, the number of arrivals per hour, the number of arrivals per minute. Then for this purpose, the Poisson distribution or Poisson process will be a good choice. And for normal distribution, if we have approximately the sum of many small and independent random variables, then that sum will be based on a normal distribution. For example, for the weight of pallet that we had in an example in the previous slide, on any pallet we have many stuff, right? And each good on that pallet has its own weight, and they are random. They are not exactly the same weight, all the goods, I mean. So because of the deviation, we expect to in general have a certain number for the weight of a pallet, but because of the deviations for all the stuff, then the weight of the pallet will be deviate around a central value, right? So yeah, because of that, the normal distribution is a good choice for that. So anytime if we see the context that there is a strong tendency for the data to take on a central value, and positive and negative deviation around this central value are equally likely, then the normal distribution is a very good choice for that context of data. The exponential distribution is directly related to the Poisson distribution. So in Poisson, we're interested in the number of events in a time unit, but in exponential, we're interested in the time between the events. So inter-arrival times. If the arrival process is based on Poisson process, then the inter-arrival times between the arrivals will be based on exponential distribution. Okay. And if we have memoryless feature in a context, or it's bounded on left and unbounded on right, again, these are the features of exponential distributions. Okay. So for the uniform distribution, if we have the symmetric feature on the data and the data are bounded on both sides, and any value within the range is just as likely as any other value, then in this context we can say the uniform distribution is a good fit. And also we can say if we have a high level of uncertainty. I mean, we do nothing about about that context, or we don't have data, but we know that in that context, the data should be between a um, certain number as the limits. I mean, we do know the range, but we have nothing about the behavior of the data on over that range. So yeah, I mean, if we are so uncertain, then again, the uniform distribution is a good choice. Okay, and for other things, for triangular, if the minimum, most likely, and the maximum values of a distribution are known and bounded on both sides, then again, the triangle distribution could be a good fit for that context. And usually for the service times, in most cases, a triangle distribution is a good fit. And also we have discrete or continuous, uniform or empirical distributions. So yeah, these are the most common distributions in simulation. Okay. So a discussion, physical characteristics of the process. I mean, the physical characteristics or features or properties on the context of data can narrow our selection on the distribution family. Okay, so for example, we can answer this question if the process is natural, discrete, or continuous, or is it bounded, natural bound. I mean, so yeah, based on the if it's bounded on the left side or on the right side or on the both sides, then we can narrow our selection on the distribution. Okay, so in general, we can say there is no true distribution for a context of data, and here we are just approximating uh, uh, those, I mean, the data set with a distribution, and so we'll actually run our simulation based on that approximated distribution. Other, we can use some statistical measures here on approximated distribution. For example, if we see that the mean and the median are equal, so this means it's symmetric, and if it's incontinuous, we can say maybe the normal distribution is a good fit for this data set. Or for example, if the mean is exactly the same as a standard deviation, so this is the property of the exponential distribution. So again, we can say with high probability, exponential could be a good fit for this data set. Okay. As I said, the exponential, normal, and Poisson distributions are so common in simulation and are easy to apply, but beta, gamma, and variable, they are rarely used in simulation because of a wide array of shapes of these distributions, so they are so difficult to analyze. For example, let's say we are analyzing a data set related to time, for example, service time or inter-arrival time. So because of the context, at first we consider the exponential distribution, not the gamma, not the variable, exponential distribution. And then if we try the exponential, and if we find out that, oh, it's not exponential, I mean, the exponential distribution is not a good fit for our data, then we'll analyze the lack of fit here. For example, see where the lack of data occurs. If it's on the tails, then we consider the gamma or variable distributions. Okay. After obtaining a family of distributions for our data set, in order to have a specific distribution, we need to estimate the parameters of that family of distributions. So we have these formulas for sample mean, sample variance, and also for different distributions. For example, for the Poisson, the parameter alpha is just the sample mean. Okay, and for exponential, the parameter lambda is 1 over the sample mean, I mean the mean time. Okay, and for gamma, for beta and theta, for beta we have a table. For theta, it's 1 again over x bar, or the mean. For the normal, so x bar or mu hat is an estimation for the mu, and also the sample variance is an estimation for the variance of the normal distribution. For the log normal, again, we do have these estimators. And for the y-ball and beta distributions, we do have these formulas to obtain the parameters. So as I said, the y-ball and beta are rarely used in simulation. The common ones, actually, I mean, for the Poisson, normal, exponential, and so on, the parameters are easy to estimate by having the formulas here. So here, so far, we obtain a family of distributions. We estimated the parameters of that distributions. So far, let's say we have obtained a specific distribution for our data set. So in the next part, in part 3 of this chapter, we will test if this specific distribution is a good fit for our data set or not. Okay, thank you.